You know that device you're watching this on right now? Well, inside it, there's a tiny little process happening billions of times a second. It is, without a doubt, the single most important trick in all of modern technology. It's the secret switch that makes our entire digital world possible. Today, we're talking about semiconductor doping.
So let's just kick things off with a pretty wild question. How do we turn a simple rock into a computer brain? I mean, silicon is basically just purified sand. On its own, it's kinda boring. So how do we get from that to the thing that powers, well, everything? The answer is this process that is both incredibly simple and absolutely brilliant.
Okay, so to really get this solution, we first have to understand the problem. Let's call it the semiconductor puzzle. The hero of our story is the semiconductor, right? But in its natural, pure state, it's a bit of an underachiever.
Look, materials are usually one of two things. You've got good conductors, like copper, where electricity just flows right through, and then you've got good insulators, like rubber, where everything is locked down tight. A pure semiconductor, like silicon, is stuck in this weird, awkward middle ground. It doesn't conduct well, it doesn't insulate well, which basically makes it pretty useless by itself.
So you can think of it like this. Silicon is a material that has a ton of locked-up potential. It has the ability to do amazing things with electricity, but the key is missing. It's just sitting there, waiting for someone to figure out how to unlock it.
So how do we find that key? Well, that brings us to the doping solution. This is the ingenious hack that turns our useless little rock into the foundation of all modern technology.
So what even is doping? It's the process of intentionally, and I mean very, very precisely, introducing tiny amounts of impurities into super pure semiconductor material. And the key words there are intentionally and impurities. We are deliberately contaminating the silicon to make it do what we want.
Now, it sounds complicated, but the idea is actually incredibly simple. You start with this perfectly pure crystal of silicon, and then you introduce a microscopic, perfectly measured amount of a different element. That's it. It's kind of like adding a single drop of food coloring to a giant swimming pool of pure water and changing its entire nature.
And just how vital is this simple little process? Well, it's been called the most important and fundamental procedure in the fabrication of all semiconductor devices. Yeah, every single microchip ever made relies on this.
Okay, so we're adding impurities. But what kind of impurities? This is where the magic really happens, because depending on the impurity we choose, we can create two totally different types of materials, which leads us right to our next section, two types of charge.
First up, we've got N-type doping. The N here stands for negative, which is easy to remember. The goal is to create a surplus of electrons. Think of it like a team of workers, where everyone has a partner, but then you add one extra person. That extra person is totally free to move around and get stuff done.
So here's how it works. We add a dopant atom, something like phosphorus, that has one more outer electron than silicon does. When it bonds with all the silicon atoms around it, that extra electron is just left over. It becomes a free electron, just wandering through the material. And since electrons have a negative charge, these free electrons can move around easily and conduct electricity. They become our negative charge carriers.
Now, the other option is P-type doping, and you guessed it, P is for positive. Here, we do the exact opposite. We create a deficit, a shortage of electrons. My favorite way to think about this is like creating one empty parking space in a totally full parking lot. A car can move into the empty space, right? But that just leaves its old space empty. So the empty space itself seems to be moving.
To do this, we add a dopant like boron, which has one fewer outer electron than silicon. This creates a vacancy, an empty spot where an electron should be. We actually call this a hole. An electron from a nearby atom can then jump into this hole, but all that does is move the hole to a new spot. So this moving hole acts just like a positive charge carrier. Pretty wild, right?
So let's just do a super quick recap. With N-type, we add an impurity that has an extra electron, and that gives us a negative charge carrier. With P-type, we add an impurity that's missing an electron, creating a positive charge carrier that we call a hole. Two sides of the exact same coin.
Okay, great. So we've made these two new materials, one with extra electrons, one with extra holes. But who cares? Why does any of this matter? Well, the answer is, it's the foundation of all modern tech.
See, the real power isn't in the N-type or the P-type material by itself.
The entire secret to modern electronics, the absolute core of it all, is what happens when you put a piece of p-type silicon right up against a piece of n-type silicon. That's when the magic happens.
This simple connection, we call it a p-n junction, is the fundamental building block for, well, almost everything. It's how you make diodes, which are like one-way streets for electricity. You sandwich them together, you get transistors, the tiny on-off switches that are the heart of all computers. Billions of these make up the microchips in your phone. They're also the secret behind LEDs and solar cells. It's all just p-n junctions.
Just how many of these are out there? Well, get ready for this. It's estimated that humanity has made over 100 quintillion transistors, all based on this simple doping principle. That is a 1 with 20 zeros after it. The number is so huge, it's almost impossible to even imagine. But it just shows you how fundamental this really is.
And this isn't some abstract idea in a textbook. As you are watching this right now, the flow of those holes and electrons, all controlled by these p-n junctions, is happening billions of times per second inside the processor of the very device you're using.
So, it all comes down to this. One simple, unbelievably clever trick, just intentionally adding some impurities to a really common material, unlocked its potential and literally built our entire digital world. It kind of makes you wonder, doesn't it? What's the next simple trick out there that's going to change everything all over again?